Oh, good morning, good afternoon, good evening, whichever is applicable to you. Welcome to part P of chapter 5. I do have two sections in part P, precipitation reaction and representing aqueous reaction. We will look at how to write the molecular equation, ionic equation, and net ionic equation. Recall in part A, the last section, we look at how to use the solubility chart or table to predict the precipitate in a chemical reaction. A precipitate is a solid. Let's say we have a reagent A in aqueous solution, all right? Reagent B where solution to form C, it could be solid, and D, aqueous, or it can be gas. What I want us to look at is the solid. The solid is called precipitate. A precipitate is a solid form abbreviated as PP. In section 5.5, we look at the precipitation reaction, which is the foundation for writing the molecular equation, ionic equation, and net ionic equation. So when you say a precipitate, what is a precipitate? A precipitate is a solid form when you mix two reagent in liquid phase, or an insoluble product is called precipitate, or PPT, abbreviation for the precipitate. For example, here is the reaction between potassium iodide and lead 2 nitrate to form an insoluble lead 2 iodide and potassium nitrate. I will use this example to show you how you can use the solubility chart to predict a precipitate. Remember, in chapter 3, we learn how to write the formulas for molecular compounds, for ionic compounds, and for acid, either binary acid or oxy acid. So this equation you see here, I will rewrite it in one. Let's say here we have potassium. This is potassium iodide, and it is aqueous plus lead 2 nitrate, and it is aqueous. Assuming that you don't know what is going to form, this is a double replacement reaction. I know we have not covered the types of chemical reactions in terms of precipitate, double replacement, single replacement. But nevertheless, here is a good exercise to practice writing the correct formulas for your compound. So for potassium iodide, you should use the periodic table. Say potassium is in group 1, iodide is in group 7, A, positive 1, negative 1. Crossover rule. That's how we ended up with that. Plus lead 2. If you look at this, lead 2 ion is PP2 positive and nitrate is NO3 negative. So these two ions here will form PP subscript 3 and then 2, and it is aqueous. So here are the reagents. That's how you can, or you should, proceed in writing the correct formulas for your reagent, because sometimes you may be given a worded chemical reaction. You're supposed to translate into chemical formulas, and then you balance the equation. This is a double replacement reaction in the sense that you should visualize this as in reagent 1, we have potassium, we have iodide. in reagent 2, we have lead 2 ion. You should see that we're cation, and then the nitrate 3 negative. That is the formula for nitrate. You should learn the polyatomic ions. Remember common polyatomic ions? Let me show you. You need to learn. Just give you a few examples of polyatomic ion. If you did not watch the previous lecture recording, these are common polyatomic ion. You should learn their chemical formulas as well as their names. So we are dealing with nitrate ion, and it has a negative charge of 1 nitrate ion. All right, you should be able to write that this is the nitrate ion we have in our question. So that's why I do have the negative 1 here. So in a double replacement reaction, the cations exchange an ion. So in other words, lead will combine with iodide, potassium will combine. The reason why I have charges here is so that I use the crossover rule to write the correct formula. So for this will form lead. It will be NO3 because 1 and 1 will cancel. So, okay, NO3, 1 and 1 will cancel, plus PPI2. How do I know that? Remember, if you have lead to ion and iodide, this will switch from I2. Common mistakes students make is just saying that this will form this, forgetting that you need to use the crossover rule. This is wrong. You can't do that when you write your correct formulas for the reagent. The question is, how do you know? Let's say here, we know now it is PPI2 plus, all right, plus KNO3. What is the physical state of solid? I mean, for lead 2 and potassium nitrate. You don't need to memorize. I know some of you may think that you need to memorize the equation. I may ask you in the exam the same equation. No. When you get to this point, you need to learn the solubility rules. There are about 10 of them, which we covered in the previous section, or you need to learn how to use the solubility chart to predict which one is a solid, which one is the aqueous, and I'll pull the solubility chart here, which you need. I think I do have down here, excuse me, this is the solubility chart. This is the solubility chart you need to learn how to use. I'll give you I'll allow you use in the quiz and exam. So, for lead 2, all right, on top we have the anion negatively charged, and the first column here we have ion. And remember, you may not have all the cations you'll encounter, but you got to use the families of element, predict how an element will react, or if it will form a solid, it will form, or if it will be soluble to be aqueous. So in our case, we have to look at where lead to ion is, and then we go across to where we have iodide. You see iodide, this is iodide, and lead to ion, it is solid. So that is where why we say it is solid. I don't want you just to remember that or memorize that. Okay, I need to memorize this. You need to learn how to use the solubility chart here to predict which one is solid, which one is aqueous. So if I look, or if you recall, nitrate ion, there are no exceptions. So it means this is aqueous. This is aqueous. Or if you look at the nitrate, except for D, it means decompose. It doesn't, as soon as it's formed, it decomposes. Rarely will you see those, like decomposition reaction, or most precipitation reaction, it will form a solid. So where we are right now with the equation is, once you write the correct formulas for your products, once you identify which one is solid, which one is aqueous, you need to balance the equation so as to obey the law of mass conservation. And you see here, there is a 2 because of the lead 2 here, we need a 2 in front of potassium iodide because of the 2 here. Don't change the subscript. Lead 2 ion, the potassium here, we have 1, we have 1 here, and if you look at the nitrates, we have 2 nitrates. Usually says 2 nitrates, by the way, and we have 1 here, so we need a 2 in front of potassium, potassium nitrate. And the way it is, the equation is balanced. We have predicted which one is solid or the precipitate. We call this precipitate. This is precipitate or just PP what? PPT, precipitate. Other questions or other problems follow the same format. You need to learn how to use the solubility chart. Why do we say that the reaction between potassium iodide, if you can see this is potassium iodide and sodium chloride. Why is it that there is no reaction? It means there is no precipitate. There is no precipitate. And what's happening here is, if we use the same approach, let's say potassium, you have potassium iodide plus sodium chloride, and this is aqueous, and this is aqueous. So if we assume that they will exchange the anion, the cation exchange the anion, this is potassium, and then there is iodide there, and sodium positive, chloride positive there. It's a double replacement reaction, and say we end up with KCl plus NaI, like that. You cannot just assume that it is solid. Using the solubility chart here, let's see potassium chloride. We may not have potassium here. Please look at it. We don't have potassium, or we have, I don't know. Let's see. We don't have potassium here. We don't have potassium here. So don't expect to see every element or all cations on the solubility chart. Use the group number. This group 1, potassium is in group 1. So let me see where they intersect with chlorine or chloride. It's right here. It is aqueous. So this is aqueous. And how about sodium iodide? Still is group 1. I don't see sodium here, but it belongs to group 1. So sodium iodide, you see, group 1 sodium, and then I see iodide here, means this is aqueous. When you don't see any precipitate, KCl plus NaI, all right, this is aqueous, you say NR4, no reaction. That's why we say no reaction for this, for the reaction you see here, no reaction. Why is it no reaction? Because there is no precipitate. Looking at the precipitation reaction, we say no precipitate form. You can learn the rules here, but I find it more effective and easier to use the solubility chart to predict a precipitate in a reaction. There is no way you can end up with, for most part, you will not end up with 2 precipitate in a reaction. But you may not get any precipitate, such as the example we just. So please remember to balance the equation again. This is 1-to-1, so we don't need to worry about anything. So this is one here, there is one there, there is one there, there is one there. The equation is balanced. The equation is balanced. So remember to write the ions. The author here uses different approach, but I like to use the charges so that I don't make mistake. When I write the cross of, I know which one I'm crossing to end up with the correct formula. So for this, right here, if I was to write this, it will look like this. K positive and I negative, PP 2 positive and N 3 negative. You see, when it is in this format, somebody might think that I'll write it KNO3, which I have seen in the lab reports. This is wrong. You are saying that potassium is in group 1, no, group 2, which is not the case. So I'll recommend you learn the charges so that when you do the crossover rule, you'll end up with the correct formula for your product, such as this right here is because of this, such as this, and it will form, 1 and 1 will cancel. So please take note of, just to clarify the difference between this and what I have on my whiteboard here. It's the same thing. You don't have to worry about that. Let's see, learning check, which solution will form a precipitate when mixed with solution of aqueous sodium carbonate. So all these, you have to look at the cation. Which cation are we talking about? The carbonate. So here is potassium carbonate soluble is sodium bromide. There is no reaction. Sodium and sodium will be just the same thing. How about ammonium carbonate? Ammonium parentheses there, and carbonate, and copper 2 carbonate. In order to predict for this, it's not something you can just look at it and just recall some of the rules. But if you use the solubility chart, you will notice that this is soluble, this is soluble, this is insoluble. It will form a precipitate. From the solubility chart here, note that solubility chart right here. Copper with carbonate. You see? Carbonate with copper, this will form PPT. The rest will just be soluble. Even if you look at ammonia, carbonate is aqueous, potassium is they are soluble. So please use this table to predict which one will be solid and which one will be aqueous. So the correct answer for this is D, based on the solubility chart or solubility rules. Let's see, write a balanced molecular equation. We're going to talk about other different equation between copper 2 nitrate and magnesium sulfide, strontium nitrate, and potassium iodide. For this, you should be able to write the formulas for your product. So here is copper 2 nitrate, means Cu subscript 3 with the 2 there. That's a formula for copper 2 nitrate reacting with magnesium sulfide, MgS. All right. Remember, magnesium is in group 2, sulfur group 6, so -2. This is Mg +2 and -2. So it's going to cancel out. copper 2 positive and nitrate negative. That's how we end up with that. And if it is double replacement reaction, that means we have Mg 2 positive and copper 2 positive and nitrate like that, nitrate. So that this and this will form a product, magnesium nitrate with the 2 subscript there, and copper sulfide, CuS, because 2 and 2 will cancel. So our product here should be CuS plus MgNO3. The question is, which one is solid, which one is aqueous, which one is solid, which one is aqueous? And if you look at copper here with sulfur right here, it is solid. Solid, which means the precipitate here is copper 2 sulfide. We call this is PPT for precipitate, copper 2 sulfide, IDE, not sulfides for the atomic ion. And this is soluble. Magnesium nitrate is soluble. We were told to write a balanced equation. Is the equation balanced? Well, 1 copper here, there is 1 copper on this side, so copper and copper is taken care of. How about nitrate? We have 2 here, we have 2 here, 2 nitrates. Magnesium is 1, and sulfur. So the equation is balanced and the coefficient is 1, 1, 1, and 1. Okay. These take care of A and B. Strontium nitrate. Strontium is in group 2. So SrNO3 with the 2, and this is aqueous, plus potassium iodide. This is aqueous, to form SR, this is SRI2 plus KNO3 aqueous. Remember to write the correct formulas for your products, okay, using the crossover rule. SIR, again, this is from this. You need to have SR2 positive, NO negative, K positive, and I negative. So that will form. That's how I ended up with those 2 products. From our solubility chart, all right, solubility chart, you have to look at strontium, which is group 2, SR. If we don't have SR here, we can use group 2. I'll say this is group 2, and then if I look at the strong iodide right here, it is aqueous, which means also group 2 will react the same way. I know this is going to be aqueous, AQ, plus AQ. We all know that nitrates, there's no exception, all nitrates are soluble. Look at the column for nitrate, except for decomposition, all are aqueous. When you have aqueous, we saw earlier on, the conclusion is no reaction. No reaction. You write no reaction if both products are aqueous. If there is a precipitate, you will indicate it as solid. You will indicate it as solid. So that's how you proceed balancing. Let's see, is the equation balanced? Strontium is 1 here, strontium is 1 here. 2 nitrates, 1 nitrate. So let's see, we need a 2 there. We just want to balance SR, 2 nitrates, and then 2 potassium by there. Even though there is no reaction. If you see aqueous, no reaction. But for the sake of it, just to balance out the equation, balance the ions, that's what it is. Please look at problem number 51 and 57 on page 207 for more practice on precipitation reaction, lastly, in this section, part P of chapter 5, I want to look at representing aqueous reaction. Remember, aqueous reaction are reaction taking place in a solution where liquid H2O is used, or just water is used as a solvent. We talk about aqueous reaction in which liquid H2O has been used as a solvent. Now, there are 3 types of equations you need to learn. You should be able to generate, and these are molecular equation, ionic equation, net ionic equation. Sorry, sometimes this ionic, sometimes it's called total ionic equation or complete ionic equation, and this is just net ionic equation. For example, here, I will show you how to write, okay? If I say write, of lead to nitrate, and this is aqueous, plus potassium iodide, aqueous. Right, I'm just making up a question here. A, balanced molecular, which is type 1 molecular equation. B, we call complete ionic equation. And C, net ionic equation. So if you are given a watered chemical reaction between lead to nitrate and potassium iodide, and you are asked to write the balanced molecular equation, the net ionic equation, this first one is just regular balanced equation. We need to translate this into chemical formulas, and this is lead to is PbNO3 aqueous plus K, this is chloride, no, not chloride, but iodide aqueous. All right. So the correct formula for lead to iodide is PbI2. Remember how to predict the correct formulas for your product is from the first reagent, there is lead 2 and nitrate negative, K positive, I negative, so that this will combine with that, you end up with the correct formula here, plus KNO3. From the solubility rules or solubility chart, all nitrates are soluble. So this is going to be aqueous, and this will be solid using the solubility chart or solubility rules. Led to iodide is insoluble, and it is shown up as a precipitate. Remember, we are writing a balanced equation. This is a balanced molecular equation. That is type 1 of reaction in aqueous. It's not yet balanced, by the way. So we need to make sure that each atom on either side of the reaction are adds up. So this is lead 1. We have one lead, we have one lead. There's 2 here, by the way, for lead 2 nitrates. So 2 nitrates, we have 1 nitrate. We need a 2 in front here. Potassium, we have 2 there. And this is 1. So that's 2 to be 1. 1, 2, and there is a 1 in front of lead to iodide. We say that this equation is balanced. This is called molecular equation. Molecular, and it got to be balanced. If you fail to balance the molecular equation, it wouldn't matter the 2 other equation. Chances are you'll get both wrong. So this is just the first type of reaction in aqueous. You need to know molecular equation. Now, type 2, you need to know is, we call this sometimes complete ionic equation, or sometimes it's called total ionic equation. Total ionic equation is the same thing. Complete ionic equation, which is N, and or here, total ionic equation. It's the same thing. How do you generate this? This you need to split. This is the criteria by which you can use to write down complete ionic equation. Split AQ phase, aqueous phase. Maybe I should write it in full. Aqueous phase. Anything which is AQ in molecular so you need to split aqueous phase in molecular equation into ions. You gotta leave anything that is solid, you don't split that. Anything that is liquid, you don't split that. Anything that is gas, you don't split that in molecular equation. So what I mean by splitting is, let me step back and show you how you split. You have to see where the anion and cation is. I split this anion cation. You don't split the solid, just leave this alone. We have to split this into ions. And remember, this is +2, this is -1, this is +1, this is -1, this is, we don't split this, so this is +1, this is -1 in terms of ions, so that what you'll end up with in this case will be lead 2, and you have to indicate the physical state, aqueous plus nitrate. The subscript changes to coefficient. You see, there's a 2 there, and then the negative, and then the aqueous. It has changed, you see. This subscript here has changed to coefficient. We retain the negative. That's why we have 2 nitrates here, 2 nitrates. Plus 2 potassium. Remember, we have 2 here, which applies to both potassium and sodium. Potassium and iodide, not sodium. Potassium and iodide. So this will be 2K positive aqueous plus 2I negative aqueous. We don't split the solid, so this will be just be PPI 2, and then this is solid plus 2K positive plus 2, and O3 negative. I split, oh, sorry, let me just get out of your way. So this is aqueous right here, two sodium, two potassiums, two nitrates. We don't split the solid. So the two potassiums, the two nitrate ions you see here from the second reagent, the two applies to potassium and nitrate ion. We don't split this, we just leave it the way it is. We split this, you see two potassiums, two iodide ions in the total ionic. We call this total ionic right here. This is right here is total ionic equation. We call this total ionic equation. So it's important to write the physical state in molecular. If you don't write the physical state here, if you don't predict the solid, the aqueous, the liquid, the gas in molecular equation, you'll have rough time splitting. You may even end up splitting something which shouldn't be split, right? So the way it is right now, we call this complete ionic equation, total ionic equation is the same thing. You leave alone the solid, you split the aqueous. Remember, subscript changes to coefficient. Subscript changes to coefficient. Then the third type of equation is called, you need to know net ionic equation, net ionic equation. You know, net ionic equation is generated by console of spectator ions in complete ionic equation. Complete ionic equation. Let me just explain what spectator ions are. Spectator ions are ions which look the same on either side of the reaction R. In other words, if you look at lead here, it's not the same as what we have on the product side. No, it's in solid form, it's in aqueous. If I look at the nitrate now, this nitrate exactly look the same as the nitrate on this side. We call this a spectator ion. Spectator ion, all right? And then there is potassium here and potassium here. They all look exact same. So what we need to do is cancel out this, cancel out that, because of these two guys, they just look the same. You see this is the same as this right here. So they cancel out. And what will remain will give us what we call the net ionic equation. So our net ionic equation in this case is P, and please include the ionic charge as well as the physical state plus 2I negative. This is aqueous, and it's going to TPI2. This is solid. We call this now net ionic equation. What remains? You know, when they say gross salary, there is the gross salary and then there is the net salary. Net is after, you know, the deduction, maybe social security and any other deduction you have from your salary, you remain with net. So here we remove spectator ions. Spectator ions are those ions which look exactly the same on either side. Question on this is not always generate the, you know, all the three equations. The question could be tailored towards, you know, asking you to identify the spectator ions. There's no way you can identify the spectator ion unless you write the correct molecular equation predict which one is solid, which one is aqueous. So that marks the 3 equations you need to learn. All right, you need to learn those 3 equations: the molecular equation, ionic equations, net ionic equation, which I've just used an example to illustrate all of them. Here is just, walking you through examples on molecular equation, list the reactants and the products without indicating the nature of the compounds. You can just look at this. It's the same thing. Please remember to indicate the physical state. Remember to balance the equation. There is no way you can memorize all the solids in the world, so that when you are given, you just plug it in. Please use the solubility rules, use solubility chart to predict which one is solid, which one is aqueous. It's going to be easier for you. And complete ionic equation, this is just splitting the aqueous. I explained to you, you can read more on this. You can practice on writing the total ionic equations. So you see here, the substitute for nitrate has changed to coefficient, and we indicate the what? You indicate the ionic charges. We don't split the solids. We don't split the liquid. We don't split the gas, all right? Just leave them alone. All you have to do is split the aqueous in molecular equation. And then lastly, the net ionic equation, all right? You cancel out the spectator ions. And remember, spectator ions are those ions which look exact on either side of the reaction arrow. You can't miss that. You can't miss that. You do it right, you will get it. Now, what remains after canceling out the spectator ions are what actually play a role in forming the solid product, in forming the insoluble. So we call precipitate. In this case, we call precipitate. For this, led to iodide. You see it's solid. And what you see here is called the net ionic equation. Net ionic equation. Look at the spectator ions. They look exactly the same thing. Nitrate, nitrate. Potassium, potassium, we call those spectator ions. You'll be asked a question on spectator ions. All right, so you can do that. Well, how to write a net ionic equation? You just have to practice. You don't need to memorize the rules we have here or the rules I do have here. Just practice how to write the net ionic equation. Practice balancing the equation. If you fail to do that, chances are you'll not get it right. So here is a learning check. Which ions, if any, are spectator ions in the reaction? So if I look at what is playing a role in forming solids, it's very easy for me to use elimination method. Silver cannot be a spectator ions because of this. Likewise, chlorine, this and this cannot be spectator ions because they are responsible for formation of the precipitate. And if I look at these two here, nitrate and sodium ions, they are spectator ions. This cannot be true. We have spectator ions. Well, this is just a summary. Please make your own notes on how to write the net ionic equation, complete ionic equation, or total ionic equation, and a balanced molecular equation. You should be well-rounded in these 3 types of equations taking place in aqueous reaction. All right. Which of the ions listed below is a spectator ion in the complete equation? All right. So you look at silver and iodide, Cs, and this can also, the correct answer is B. Correct answer is B. Very easy to learn that. Write a balanced complete ionic and net ionic equation for sodium phosphate and nickel 2 chloride. You can write this. It's very easy. All you have to do is balance the equation. All right. The equation is not balanced, by the way. You need to balance the equation. All right. If you look at the equation, it's not what? It's not it's not balanced. So you need to balance the equation first in order to do it, in order to write the balance. Let me just minimize this. I'll walk you through that. So if you look at the equation, it is Na3 sodium phosphate, this is sodium phosphate, plus nickel 2 chloride, aqueous, going to Ni3 nickel, this is nickel 2 phosphate, should be nickel 2 phosphate, by the way. There should be a 2 there. I missed that. But remember, it's nickel 2. I know it is nickel 2 because chloride is -1, and these two came from nickel. So here there should be nickel phosphate is +3. I mean -3. These 3 came from phosphate, and plus NaCl like that. This is aqueous. And we have been given, by the way, the physical state. Nickel 2 phosphate is insoluble, so it is solid. The way it is, the equation is not balanced. Look at here, we have 3 sodiums, we have 1 here. So using trial and error, we need a 2 in front here and a 6 in front here, so that we read this as 2 sodiums and 6 sodiums. 2 times 3 is 6 sodiums. We have 6 sodiums right there. And here we have 2 phosphate, 2 phosphate. Nickel 3. We have 1 here. How do we make it 3? It's by putting a 3 in front here, so that the 3 applies across. You read this as 3 times 2 chlorines, we have 6 chlorine, and the way it is, the equation is balanced. So for complete ionic, look at this, complete ionic equation, we split the aqueous. So we're gonna split this, we leave alone that, we're gonna split that. So that this will be 6 Na positive aqueous plus 2 phosphate PO4 and the 3 negative, it's aqueous. The 2 applies to phosphate as well. Plus 3 nickel 2 ions aqueous plus 6 Cl negative aqueous going to nickel 3 phosphate PO4 with the 2 there, remember solid, plus 6 Na positive aqueous, 6 chlorine aqueous. So what I have here is complete ionic equation. I split this, split that, we just leave alone that. And then net ionic equation here, all right, net ionic equation, you need to cancel what we call spectator ions. What are the spectator ion? In our case, what is not responsible for formation of the solid here, it is sodium and sodium, chlorine and chlorine there, chloride, and what will remain is 3 Ni 2 positive aqueous plus 4 phosphate, it's 2 phosphate, so and then a charge of -3, so aqueous. We have nickel 3, nickel 2 phosphate, by the way, this is 2 and it's solid. So what I have here is net ionic equation. We call this net ionic equation, net ionic equation. We call that net ionic equation. All right. So here, please remember to balance, right balance. Every time you see right balance, that means the equation is not balanced. You need to balance it out. You need to balance it out. Look at problem number 55 on page 207. That's a good practice. Please, you want to practice more on writing the complete and equation and equation. Look at problem number 55. Acid-base and Cass evolution reaction. There are two other important classes of reaction that occurs in aqueous solution. Those acid-base reaction, where an acid reacts with a base to form a salt and liquid H2. And then there is Cass forming reaction, Cass forming reaction. Acid-base reaction sometimes we call neutralization reaction. And you need to remember that in acid-base, a salt plus H2O or just water. Let's just call this water. Acid plus a base will give you a salt and water. The one criteria I look for that. But for gas producing, you have to see what reagent are involved. Some reaction keep hydrogen gas, some keep hydrogen sulfide, some keep carbon dioxide gas. Gas evolving here is evidenced by bubbling, the viscid. For example, dropping antacid in H2O, you'll see some bubbles. It's an evidence that the gas is being produced. Many of cast giving or cast producing reaction are also acid-base neutralization. Please proceed to part C of the lecture.